website? Okay. Okay, so until now, we were using this software apps in Sim to get a feeling and understand how do we make images. But obviously, that's not the software that we use to reduce ALMA data. The package that we use is called CASA. And yeah, the software app Sim is quite convenient because then you very quickly can see the effects of all the parameters that are playing a role. Because if you are trying to learn this intuition by using normal observations, it will take you forever because the files are extremely large, they are very heavy, and you need to make a lot of iterations. So that's why we used first that previous software, and now we will jump into CASA. Okay, so I think we kind of managed to put the CASA package in every computer here in the room. I will show you later. Well, this is basically a summary of all the websites related to CASA. There is a guide for getting started with CASA, how the interface works. This is the getting started summary, and then there are several guides and the cookbook. In the cookbook, you have all the information of the tasks, everything that you can do with CASA. It's very handy. And then there is a particular very useful resource that we will be using, which are the ALMA guides, which are several examples of different science different targets that have been reduced with CASA. And they explain there in these wiki pages, step by step, all you need to follow to get to the final image. And there are many different targets there that come from the science verification data. And this is what we will be working on. Okay, just before going to work with the science verification data, what you usually do, well, you can do for when you want to work with ALMA data is just go to the archive and search for what's in there if you are interested in a particular target and you want to download the data and work with it. So that's the interface of the archive. And just to show you here that you have it there, you can put, if you want to search by project code or by source name or whatever, there are many fields to do the search. And once you make the search, it shows you all the things all the data sets that are in the archive. So you can go and select the data you want. And in the next, you can inspect what's in there. And you will learn, perhaps not today, but on Monday, what are the different what is the folder structure here? So if everything is normal for that data set, you select the data to download, and that data comes together with some scripts that you download to your computer, and then you run the scripts that are provided to get the results. So if the data was good and was observed in normal conditions, in regular cycles, there is always attached a Python script that you run in CASA to get the calibrated data to get to the final images. So you just need to reproduce again that script to get to the final images, and then you can start on with your analysis. Of course, if the data set was complicated or was not of good quality enough, you don't have those scripts because the data was classified as not good. And if you really want to use that data, then you have to fight yourself with all the data reduction. And then, once you select the data, in the next step, it gives you several options to download the data with a script or with a GUI or whatever. Okay, today we are not going to use, for the moment, data that is in the archive. Perhaps, next week we will try to. But instead, we will be using the science verification data. So they selected several targets, a lot of them actually, to demonstrate the capabilities of ALMA. And well, if you don't like the one, we will go through all the images, of course. If you don't like to do the analysis for the target that I suggest, feel free to grab some other target and do the same. After all, it's a matter of learning what are the products of ALMA, right? So I will propose you several steps to analyze the data of TW Hydra. But you can do the same for another of the targets if you like it more. OK. So what are we going to do? What are the data products that we get with ALMA? Let's say that we observe a line, like the CEO, blah, blah, blah. Then we will ask Alan, what does it really mean again? But yeah, we have several bands in ALMA. You can choose to observe the continuum, or you can choose to observe in a spectral mode. Spectral mode, you basically are making channels in frequency. So you have frequency, and what you do is you bin the frequency range, and then you measure the sky brightness in every of these channels.
And the sky brightness of all the images?
Yeah, for every channel you can choose. You make you measure the visibilities for every bin, and then you can choose to make an image for every one of these channels. Or if of course, it's more, if the signal is very low, you can choose to average every 2 channels and make an image out of it, or 3 or 4. But in principle, if it's good data and a high enough signal to noise ratio, then you can make an image out of it. So at the end, what you get is a data cube which has 3 axes. Okay, so you have the usual coordinates. Your source is here. And then a third coordinate, which is frequency or velocity. Okay? So you have one image for each one of these velocities. Okay? One image here, another there. I'm not very good in drawing, you can see. But basically, you have a 3D data cube. Okay? And this is what we will be able to explore later. Okay. So first we have the 3D data cube, and we can visualize it, velocity per each one of velocity per velocity, or we can decide to collapse it, to integrate along the velocity axis to have a collapse map of my source that contains the information of all these channels. Okay? We can do several things, as you will see in the next slides. Yes. So this would be like a way to visualize the 3D data cube that I was talking to you about. There are a couple of packages that you can use, but within CASA, we will be able to also see those channel maps. We can do what I was showing to you, line profiles. So if we have our data cube, okay, this is velocity, this is we have our source, and we can decide to select an area, and extract all the information along the velocity axis, and then we get a profile. Okay? We can choose several areas, regions in our image to get the profile. Okay? You will play with that later. It's part of the exercises. Yeah, this will be a visualization of the data cube per channel. So we have a map at every velocity, and it tells you basically if you have a cloud of gas, it's telling you at which velocity it's traveling that gas. Okay. So you are making cuts in the cloud for every velocity. And here it's to show you that we can collapse those channels maps to get what we call the moment maps. The first moment will be like to just collapse all the channels in one single map. But then you can also measure what is the velocity of the pixels in every of these single maps, and then make an average. And that's what you will get. That would be the average velocity of your target. And this would be the classical result that you will get for a rotating disk. So imagine that we have, let's say, we have a gas that emits a line at a certain frequency, so at a rest frequency. But that cloud is it's flying at a certain velocity with respect to us. So that velocity will have, so that signal will have a redshift. Okay? Okay. When we point to the cloud with our telescope, we are only sensitive. It's okay. It's okay. It's not too bad. Okay. You don't have that. Oh no. It's the wrong version then. Oh. Okay. Sorry guys. I will send it again. That's too bad. I will fix it. Yeah, you have to put a bit of imagination to understand the rotation of a disk, but it's quite easy. The idea is that you have a cloud that is traveling at a mean, let's say, it's at 200 kilometers per second with respect to us. Okay? So you have the disk, that target that is at that distance. But then at the same time it's rotating. Okay? So then you have a redshift with respect to us, a main redshift with respect to us, but the part that is rotating towards lower velocities will appear blue shifted with respect to the central velocity of the disk. And the part that is going backwards will have a redshift. Okay? So you have to imagine that if the disk is edge on, totally edge on, you will only be seeing the gas that is flying towards you and the gas that is leaving, it's going to the back. Okay? So the one side of the disk will be coming towards us in velocity, and the other part will be going farther away. So with respect to the main velocity, you will have...
The red and the blue are redshift.
Yes. So this part, so the mean velocity of the disk is here. And this part is traveling away, and the other part is traveling forward to us. So it's
no movement.
Would be, yes, no movement with respect to the disk, to the velocity of the main cloud. Yeah, yes, that's correct. So that would be what you could see if the disk is edge on. But yeah, we have projection issues here. If the disk is perfectly edge on, you will be able to see all these slices in velocity. But as soon as you start turning your disk and put it in face on, you will not see those velocities anymore. If you have a very infinite, so a thin disk, which is completely face on to us, you will not see any rotation. You will just see a layer of gas that is at a certain redshift. But you will not be able to see that velocity range. Okay, so when they are analyzing rotation patterns of disks, they have to do this deprojection and with respect to the image that we are observing. Okay. Okay, so you don't have this image. Okay. It's very easy in any case. So the moment zero is just if we have the flux profile with respect to velocity or frequency or redshift. Sorry. We integrate that flux, and that give us the moment zero. So it's a total amount of flux that we are receiving from that source. The first moment map that I just showed you is an average of the velocity of that gas, basically. Okay, we are making an average of the velocity, and in order to get that average, we weight every pixel by how bright it is in your channel maps. Okay, it's just a weighting, a way of giving more weight to those parts that are brighter in your channel maps. And finally, we have the second moment, which is a measure of the velocity dispersion of the gas. You will see it with the TW Hydra if we manage to. And this is an example of a galaxy that is rotating. This galaxy, this is neutral gas. So the moment zero map, it's a collapse of all the channels. So you get the amount of gas that is in there, in the disk. The first moment map is the average velocity. So you can see, like there is one part of the disk that is blue shifted with respect to the mean, and the other part is red shifted. And finally, this is the velocity dispersion of the gas. So here you can see that the gas that is at the center of the galaxy has more velocity dispersion than the one that is in the outer parts of the disk. So now I think perhaps it's time that we can try to open CASA and take a look to the images that we have placed in the computers there. So if you can go to, I think to this one you have it in your slides, right? Okay. And I think the exercises should be there as well, right? So can you, do you see your folder in your home directory, which is called CASA version, something like that? And you can extract it. So we tried to do it, but for all the machines, but we couldn't. What are you trying to do? ¿Está suelto? De aquí. Ah, y por eso daba problemas de. Podemos copiar. What? Ah, sí. So when you open Casa, you get, it should be equivalent. It should open something similar like this. Didn't do that? And then /casa should give, because they are trying to, in the latest versions, they are trying just to avoid the Casa Pi and Casa, just to a single one. Because before it used to be like the Python environment was different. Yeah, but it's not going to, it's going to give you a window. It's okay. Yeah, we should be able to. So you got a window there. That window is very important because it's the logger. Here, in the log window, you will see all the messages that Casa is telling you about all the tasks that we are trying to run. Now, can I recover the? Oh, yes. So if you, do you all have, guys, the Casa open? Have you also decompressed the images folder that you have there? You also have a folder called images, and inside of it there are a lot of compressed files. You don't have a folder called images in your home? She said yes, Vanessa said everybody. So in the Casa folder, sorry, the Casa folder is just the. So you all have the folder images, and you have the images that we have put there. These are the output products of the data deduction of all the science verification targets. And these are the ones that you will be able to open in Casa with a viewer later. So that I suggest, as an example, and for the exercises, this target, which is TW Hydra, in band 7. And you have here the zero moment map, the velocity map, and I guess the velocity dispersion of this disk. But in the folders, in the images folder, you have other targets that you can also perhaps like better, like a galaxy or something else, or an Einstein ring that there is there. Perhaps you want to do the exact same exercises that I proposed, but for that target is also fine. So the idea, there is also one paper about this data, which studies the kinematics of this CO disk. And yeah, you can compare what you see in the data with the results. So if you can have access to this data, to this paper, sorry, you will see all the images that they put there for the analysis. The idea is that you get the skills to create similar outputs from the data cube. So you should be able to make a PV diagram of the disk and the moment maps and show it in a similar way. Yeah, the deadline for this exercise is again the day before I leave. So I think I'm not sure what was the time that we agreed here, 1 a.m. on Thursday or something like that. Okay. So I propose you here an example on how to visualize on the channel visualization to make channel maps. For this particular target, you can follow the CASA guide. Here they explain step by step how to do the analysis of this disk. Because we have not reduced the data, it's already reduced. You just need to pay attention to how to display the data, basically. Should be very straightforward. So then I mentioned this folder, but actually in your CASA version gives problems. When you open these files, it doesn't read properly the beam size. So it's reading a beam size that is almost as big as the sky. So then it's not showing the images correctly. And for that reason, I asked Vanessa to copy a folder called TW Hydra in your home directory. Sorry, inside the images as well, right?
No, it's another folder.
Okay, so instead of opening that was last minute, sorry. Instead of opening this, instead of opening this one, just go to the folder that I just mentioned, and there you can find all the moments and the channel maps. Okay, and then here I just suggest that you make the moment yourself, and the things in red is the one that I would like you to upload. So basically, make a PV diagram with a caption explaining what are you showing there. Because when you make a radio image and you put some contours, you have to write down, in the similar way that they do in their paper, you have to write down what is the color scale that you are using and what are the contours. And to be consistent, you have to choose the contours according to the RMS that you have in your images. So first you measure what is your noise, and then you start making contours starting at the noise level. Okay? So this way we understand, okay, this peak compared to the noise level is like making a topography map of the Earth, let's say. Okay. And then, yeah, I would like to ask you to comment on the models, the kinematic models that they try to fit in this paper for this disk, because they mentioned, well, they try to fit 3 different kind of rotating models, and finally they discuss that one of them describes the data best, so you can comment on that as well. Okay. So yeah, these are the exercises. So I think now we should just go to try to open the viewer in CASA. is my... Okay. So you can try to open the viewer, as I did. You write viewer, parentheses, and it should open a new window for you. Or you can also do viewer, go to the folder and do viewer, name of the file, and it should open it as well. So you go and open the viewer. Have you selected perhaps the... I'm trying to open it as well. We can try just to play. This should be the channel map, the data cube. And here you can see which velocity range is covering. So this data cube is going from -4 to 10 kilometers per second. So in that velocity range, you have slices in velocity. You have one image per slice. Have you opened any of the files with CASA already?
This concept open. No.
Ah, yeah, sorry. Because you can choose to open the image in different ways. The normal one is raster image, which is going to give you a color scale image from the file. Okay? Another option is to do contour map. If you choose contour map, it's only going to plot contour map lines on it. So I suggest you open it as a raster image. Okay, so then, let's do that. You should get a window like this. Do you? I think IMAP is not helping me very well. Sorry guys, it's not giving me like... Okay. So it's showing you, perhaps you see, can you go? It's showing you a panel that says channels with several arrows. You can do play, there, play, and you should be able to, see? Mm-hmm. Okay?
I haven't done anything here.
Raster image, okay, and now you go there, and then you do play. Sorry guys, it's giving me, now. Do you guys get this working? All of you? So you can, I think it's quite fancy. Yeah, you choose raster image, and then, yeah, you can go play. Okay. Yeah. So you can see in the top right corner the velocity of each one of the channels. When you press play, yeah. Okay, now for instance you can go and open the zero moment map to see as well how does it look like. Or you can leave it playing forever as well. You can try to open the moment zero. But now I think you have to, yeah. When you open another image in the same display, now you don't see it, right? Have you tried to open the zero moment and you see nothing, perhaps? Well, because I have to, here I have the data cube, and I also open the zero moment map. I open both. So you have an extra window here, which is called images, in which you can choose to move from one to the other. So if I move to the left, I am seeing the channel maps. If I move to the right, I'm seeing the zero moment. Because you may think that when you open a new image, it's not shown, but it should be there. Yes, sí. El cero, si la abres, raster image again. If you go back, you don't see nothing, right? But it's actually there. The only thing is that you have to choose, select that, and bring it to the right. It's not working. And if you press that, okay. It doesn't like the mouse. Too bad. So this is basically telling you that you are, if you go to the, you put zero, you go to the data cube. If you put, this is useful because if you want to make overplots, like compare the zero moment map with the channel maps, you can show more than one image at a time. You can also now go and try and open the so I have opened it's going a bit crazy. So now you can go and open the, doesn't show it very nice in my screen, but you can open the first moment map, the one that contains the velocities. Have you opened it already? This one, that it's named mom0 weighted, is the first moment map with the velocity information, and the other one is the velocity dispersion. So you can also try and open it. Oh. I don't know why it's not showing me like super big. Okay, the idea is that you yourself, as an exercise, obtain the zero moment and the first moment map and the velocity dispersion from the data cube, okay? Because now it's done already, but the idea is that you do the calculations yourselves and that you get some spectra as well. You can also go and try to open the other images that you have in the folder. I would like you to really go and explore the same way as I'm showing here with TW Hydra. Try to open the SDP81, which is an Einstein ring. Open it there and visualize it, or the antenna galaxy, the other ones that you have in the image folder. So I really think you should try and take the time to go through them. So let's see that I'm done with TW Hydra, and I go to no, it's so the idea is that you use the it's a broken link. The idea is that you go to the CASA guide of TW Hydra, and you can follow the steps here to get the moment maps. So here you have, the data cube, and then here it explains you how to visualize the channel maps. You have done already that. How to get some spectra through it with the viewer. We will do that together in the next time. And then how to make a PP diagram as well. Here is how to calculate the moment maps. For that, what you do is you can do it from the viewer. The viewer itself has all the task already implemented there to do the moment map analysis with your mouse clicking, selecting areas in velocity and ranges in right ascension and declination. But you can do it from the console, from the terminal yourself, by calling the CASA task directly. And then for that, you will go to the Python command. Here you can write any Python command that you like. It would work. So it's the CASA Python environment. So you can put your Python code here and also call all the CASA tasks. So I think if you do task list, here you will have a list of all the CASA tasks. They are all in the cookbook as well, but here you can code Python normally. So in that case, you can use a part of this part of the code. You can copy paste in the terminal to calculate the moments from there. But you can also do it in the viewer, selecting regions and going to do it visually if you wish. The advantage of doing it from the terminal is that then you keep the code forever. Okay, have you gone and checked the other images as well? All of them? What time is it? Shall we? 10:30. So then we can perhaps take a break.
una ventana.
¿Cómo qué?
Pues mira que está... No.
So, shall we take a break of half an hour now until 11? And then we keep working later? Okay. So let's